Recording is rolling. Welcome to Wednesday, May 10th. Okay, so we're going to continue on final exam review. We might have a few minutes at the end of class, possibly kind of get you guys started on paper roller coaster, but if not today, then let's have you guys do it tomorrow. Okay. Some other announcements. Monday, if you're my first 4 periods, you guys are going to be relocated because I'm going to be proctoring an exam in this classroom. I just got this email this morning. I don't know where you guys are going to be relocated to yet, but when I get that information, I'll let you know. Okay, so, all right, so you guys good with that? And then, okay, so if you're watching this video and you're in my 6th or 7th period, then just go ahead and show up to class like normal. Okay, and you guys remember also, senior exams are coming up in a few days. So senior exams are Monday, Tuesday, Wednesday. And the science senior exams are on Tuesday. And since this is a science class, if you're a senior, when you're taking this exam? Tuesday, May 16th. Okay. All right. So everybody good with what we're doing? We're good? All right. So let's pick up where we left off. Right. I think we did this last one. Noise canceling earphones are an example of. Here, I'll go ahead and throw the notes up here anyway. I suppose you have a hot string. Right? And I send a wave. Oops, let's get the rest of that there. Right. And I send a wave pulse. Oh, what's wrong with that pen? All right, so, going to the right here, and I send another wave pulse going to the left there, right? Okay. Now, when they cross over, like crest to crest, well, I guess crest to trough, right? What's it going to do? It's going to be just canceled out like that, right? And that's true, right? That there's a name for that. It's called what? Destructive interference. You guys remember destructive interference, right? And actually, if you want to keep rolling the story ahead even further, these wave pulses will actually pass through each other and just keep on going this way, which looks really weird. I played a video of you guys one day. Somebody did this with a rope, right? Okay, right? Guys that? Now this is a transverse pulse, like a transverse wave. You guys know sound is longitudinal. That's like a pressure wave. But the same principle works with sound. So noise canceling earphones, what they do is they take the ambient sound, they invert it, they cross it on itself, and it pipes 0 sound into your ears. The speed of sound in dry air at 20 degrees Celsius is 340 meters per second. You guys have seen this number before. So speed of sound, 340 meters per second. That's important. How far away is a jet plane when you notice a 2-second delay between seeing the plane and hearing it? Ooh, 2-second delay. I'm going to change the story, but it's going to be the same math. Do you guys remember if you see a lightning strike and then you hear the thunder and you count the delay between the lightning and the thunder, you can figure out how far away the lightning is? This is the same thing, except replace lightning with jet, right? So you could use an equation that I bet you guys knew before you ever step foot in this classroom, which goes like this. We're trying to figure out how far away, that's like a distance. We know the speed of sound, and we know the time delay. Distance equals speed times time, right? Let me go way back to August. Let me remind you guys that you knew this before you ever even met me. Suppose you're driving north on I-95 at 60 miles an hour. 60 miles an hour. And you do that for 3 hours. How far have you gone? 180 miles, right? 60 times 3 is 180, right? Now, we're not using miles and hours, we're using meters and seconds, but it's the same idea, right? Okay, so what they tell us here? They told us the speed of sound is 340 meters per second. That's the speed right here, 340 meters per second. And they told us the time delay was 2 seconds. Right? Yeah, if you're watching lightning strike and then you count a 2-second delay before you hear the thunder, right? Guess that? X equals, right? And that's 680, that would be meters. Right, would that be true? All right, any question? Any question? Right, guys good? All right. Which of the following are fundamentally different from the others? So let's read off this list because 4 of these are categorically the same and 1 is just categorically different. Okay. We got X-rays, radio waves, gamma rays, sound waves, light waves. Which one of those does not belong with the others? Sound, exactly, sound. Because the other 4 are all what kind of wave? yeah, electromagnetic waves that travel at the speed of light, or they're transverse, right? But they can also go through a vacuum, right? But none of those are true for sound. Sound is a pressure wave that call it longitudinal, right? And it needs a medium to go through. Right? It also travels much, much slower, right? Many orders of magnitude slower. Right? So all those make sound different from all those other options, right? Okay. And those other ones have different frequencies and wavelengths from each other, but they're categorically the same idea, travel at the speed of light. The main difference between a radio wave and a light wave. Guys, do radio waves and light waves travel at the same speed? Yes, they do. They all travel at the speed of light, 3 times 10 to the 8 meters per second. So that's not a difference. That's the same. Now, there are two differences between radio waves and light waves. So two good answers, and maybe they're not both on here. What and what? Frequency, which was not given as an option, and wavelength, which is frequency and wavelength, right? Isn't that the two differences? Isn't it true that here, like a radio wave, radio has a long wavelength and a low frequency, right? Versus light, like visible light, I'll say visible light, right, has a short wavelength and a high frequency, just relatively. Like if I'm just compare those two, right? Guess that, right? But they all move at the same speed. Speed of light is wavelength times frequency. Right? You guys remember that too? Remember that? Okay, there we go. What else I want to say here? Right. Oh yeah, so for radio waves, think like several meters might be the wavelength, but visible light, we're talking about like hundreds of nanometers. And different wavelengths can correspond to different colors. The main difference between a radio wave and a sound wave. Ooh, actually, you guys just sort of told me this one. Radio wave and a sound wave is, look at those answer choices. What do you think we're looking for here? I'm going to say basic nature. Yeah, basic nature. Yeah, those are fundamentally different ideas. Radio waves are EM waves that travel at the speed of light through a vacuum, possibly. Sound waves are pressure waves, longitudinal, that need a medium to go through, travel much slower. Compared to speed in air, the speed of light in water. Ooh, do you guys remember something like index of refraction? Right, so here, we're getting to talk about refraction. So this is like air and water, right? Air, the index of refraction might be like 1.0. Index water, it's like 1.33, I think is what it was, right? So you have a normal line, right? You got a ray of light coming down, it's going to refract. Right? But why does it refract? It refracts because it slows down. There's a whole process. There's an equation called Snell's law, which you don't actually have to navigate for this exam, but right. But here, index of refraction is what's the speed of light in a vacuum compared to the speed of light inside that material. Right? That's what these numbers are. Okay. Right. You guys remember that? Okay. So does light slow down in water? Yes, it does. Okay. It also slows down in glass, which allows refraction. Here, let me show you guys another demo. Okay. I got this magnifying glass here. Okay. This is a refractive lens. And part of what makes it work is the fact that light slows down inside the glass, which allows refraction. It's curved into a lens shape, so it can magnify. If an electron vibrates up and down 1,000 times each second, that generates an electromagnetic wave with a what of what? Guys, 1,000 cycles per second. What is that called? Exactly. Frequency of 1,000 hertz. There you go. Say frequency of 1 kilohertz. That works too. Okay. Great. 1,000 cycles per second. That's a frequency of 1,000 hertz. Okay, you guys remember that? If two polarizing filters are held with their polarization axes at right angles to each other, the amount of light transmitted. Okay, I've got the answer right in front of me. I got a couple of let's go beat it. Okay. I got a couple of polarizing filters. Let's say this one's vertical and this one's vertical. Okay. So it only allows light through vertically. Okay, cross them over each other, vertical, vertical. Pretty much most light gets through, right? But what if I take one of these and turn it 90 degrees? Now we got vertical versus horizontal. Now how much light's going to get through? None. Look at that. Right. So there's when they're parallel. There's when they're perpendicular. Right. You guys see that? Right. So at 90 degrees to each other, no light, zero. You guys see that? Okay, colors on a TV, colors on a photograph, colored dots that make up a TV screen? I want to do these three questions kind of together, right? Maybe a little bit out of order. Is it okay if we try to skip ahead and roll back? Right. But let's start with this third one here. Number 65. The colored dots that make up the color on a TV screen or a laptop screen or your phone screen. If you get down microscopic, there's only 3 bulbs. And what colors are those?
Oh, I was gonna ask, like,
Okay.
I didn't get the,
Oh, study guide?
yeah, I didn't get it.
Okay. Here you go. All right. So guys, what are the 3 color bulbs? The only 3 color bulbs on your phone screen? Red, green, and blue. There you go. It's called the RGB standard, red, green, blue. Great. Hang on a minute. If there's only red, green, and blue, let me poke around with that a little bit. How do you make yellow? How does yellow show up on your screen? You flash the red and green, right? And then from a distance, it looks like yellow. You don't have to memorize that. I'm just saying. Hey, how does your phone make white? How is white light? That's all 3 of them lit up together. If they're all flashing, that makes white light. How does your phone make black? Just turn them all off. Yeah, turn them off. Okay, right. Now, that type of color addition, whoops, I'm sorry, I gave away the answer I was going to ask. That's called color addition, isn't it? Color addition. The more bulbs you have lit up, the closer it gets to white light. Okay, now let's cycle back to the ones I just skipped. Colors on a TV screen or your phone screen result from color, what was the answer? Addition. That's color addition right there, isn't it? Color addition. Right. Right, guys good? Right. This question, color seen on a photograph, or how about your ink printer or paints? Now that's a different process. That's called color what? Subtraction. Right. Let me add my own question here that could have been on here, but guess it missed the mark. Do you guys know the 3 colors in your color printer? No, besides the black, you have a black cartridge, of course, and then you have what?
Magenta, cyan, and yellow.
Yeah, that's what you guys were going to say too, right? Yellow, cyan, and magenta, right? Okay. Now, what if you have what if you put all 3 of those colors on your paper at the same time? What if it prints yellow and magenta and cyan? What color does it make on your paper? Black. That's color subtraction, because now the more inks you're applying, it's like subtracting out the color, right? The law of reflection. Law of reflection says, okay, here I've got it right here. Right. So suppose you have a flat plane mirror. You guys see like I have a flat plane mirror right here, right? And I'm gonna bounce a light ray off it. So I got this boing light ray, okay? And I'm measuring with respect to this normal line. You guys see this dashed normal line, like perpendicular to this mirror plane surface, okay? So suppose my angle of incidence is like 32 degrees, right? Doesn't it reflect also at 32 degrees from that same normal line? Right? That's the law of reflection. The law of reflection says that the angle of reflection matches the angle of incidence. Okay. Okay. Yeah. Go ahead. Okay. Now, it could be that maybe your mirror is not a plane mirror. Your mirror might be like a curvy funhouse mirror. And if that's the case, then this law still applies, but it just applies like per unit section. Right? And so you'll like a warped reflection. Okay. Look at back at the spoon, for example. The shortest plane mirror that you can see your entire image. Does anybody remember the answer to this question? Suppose you're 6 feet tall. How much mirror do you actually need to see your entire reflection? You guys remember it's like 3 feet? Right. And here, I'll just flash up my notes here. So suppose I got this guy standing in front of this plane mirror. This could be a plane mirror, like a dresser mirror. Right. Now, I did make the dresser mirror the same as his height, but that's not the answer we're looking for. Right. I just did it just for completion. Right. And he sees his reflection. You guys see his reflection kind of dashed off here, right? And here's his eyeball looking at his reflection. And I drew some light rays. So he looks up and he sees the top of his head. Now, that's extrapolated. That appears to be his reflections from there, but it really came from boing, from this light ray that skirted the top of his head this way. Boing, law of reflection. Okay. He looks down, he sees the bottom of his feet. But really, that light ray came from boing, from the bottom of his feet, like here. Boing. Is that? So do you guys see that all the mirror he really needs to see his entire self is just this bit right here? Right. Now the catch is it has to be positioned correctly. If it's like down here, you can't do it, or up here, you can't do it. It has to be positioned right there. Okay. Now let's make some measurements. So his full height is I've got a tad over 6 centimeters. You guys see a little over 6 centimeters tall? You guys see that? Right. Now what's this section of the mirror that's all he needs to see his entire self? Ooh, guess it's a tick over 3 centimeters. Hey, 6 centimeters, 3 centimeters. Guess that? So what's the general answer? Half your height. Yeah, the amount of mirror you need is going to be half your height. You guys do that? Okay. A rainbow nicely illustrates an example of refraction, reflection, both. What are you talking about here? I think this might be the one question that I never exactly covered in class, but we'll cover it here, and then this will be complete. Right? Here we go. So here's you. You're an observer. You look over to the right. And, oh, hey, there's a rainbow. Right. Now, guys, whenever you see a rainbow, where is the sun relative to where you're looking? Always behind you. It's always behind you. So I drew the sun like behind where you're looking. You're looking over to the right. There's your little eyeball right here. Okay. There's the observer eyeball right here. Right. Okay. This rainbow is actually like a circle shape, but the horizon cuts off the bottom half of it. Okay. Okay. Now, why do the colors like spread out like that? Well, let's go through the process. Let's see, like this ray emerges from the sun, right? And I meant to mention one more detail, right? Because where we see a rainbow, there's a lot of what in the air? Water droplets, moisture, humidity, right? It's usually after a rainbow, right? Okay, so here comes this ray of light. It refracts off this raindrop. I blew up my raindrops, make them really big, just to make this obvious. It reflects off the back of the water droplet, and then it refracts one more time as it leaves the water droplet, right? And then into your eyes. You need refraction and reflection. You guys see you need both those processes to make the rainbow? Okay. And so why then do the colors spread out? Well, every wavelength of light, and you guys know that every color is a different wavelength. Every wavelength of light refracts at a little bit different angle. You guys seen like a prism? If you shine a light through a prism, it'll like the colors spread out. And that's the last thing that makes this work. So something to do with the refraction bit of that. Okay. Right. Now, I want to mention more about that the light spreading out, because I think that leads to the next question. You guys see this refractive lens? Okay. So this refractive lens, there is refraction. You can use it to magnify, just like I am right here. Because every color refracts at a little bit different angle, do you think the colors spread out a little bit? They will. Now, it's not maybe super obvious just looking at here, but what if I use this to make like a telescope, like a pirate telescope, right? Maybe I need a couple of these. Okay? The first telescopes hundreds of years ago, that's what they did. Just a couple of days, put them together, look up at Jupiter. But the problem is that Jupiter was kind of spread out for that reason. That's called chromatic aberration. Okay? Do you guys remember what the solution was that solved chromatic aberration? Like, why can the Hubble take a picture of Jupiter and it looks really crisp? Because it doesn't actually use a refractive lens. It uses a what? Exactly, a concave mirror. Right. This is a concave mirror. I guess it's like a concave mirror. Okay. Do you guys remember who invented the concave mirror reflecting telescope? Isaac Newton. Right. Right. Let's check here. Yep, that's exactly the next question. Chromatic aberration occurs because different colored light rays, and we're looking at different colored light rays, refract at different angles when passing through a lens. Yep. Oh, did I? All right. Oh, yeah. Thank you. Thank you for catching that. Okay. So a person standing waist deep in a pool appears to have short legs because of what? Refraction. Okay. Let's go back to my picture right here. Right. Suppose this is like a swimming pool. Okay. And I got here's the bottom of the pool right here. Right. Here's the water line. So I got water. Oh, water and air. I already labeled that. Water, air. Okay. And I got this guy standing like right here. Got this guy standing right here. Right? Okay. Now, if there's an observer over here, let me draw an eyeball to represent an observer. Right? This guy's looking, and what he perceives is where this light ray came from is like from back here. Right? So he thinks that this guy has legs that look like this. Right? Guys see that? So this guy appears to have short legs from this observer's point of view, but really that light ray came from way down here. Right? So that's refraction, isn't it? Refraction. Okay, you guys get through number 70? We're good? Right, any question? Okay, number 71, a magnifying glass underwater will magnify how? More or less? Okay, so here, I got a magnifying glass right here. Now, part of what makes a magnifying glass work, right, is refraction, and refraction happens because light slows down inside the glass. Right? and that has something to do with index of refraction. So index of refraction of glass. Right, now there's different numbers, but I'm just gonna pick one. Let's call it like 1.5, for example. 1.5. Right. Index of refraction of air is 1.0, and the index of refraction of water is like 1.33. Okay. So let's think about how much refraction there would be, and therefore how much magnification there would be in these different scenarios. Right. If you have this magnifying glass in the air, we're comparing these indices of refraction. 1 compared to 1.5. Is that true? You could run Snell's law and figure out blah, 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 right? But if you hold this underneath the water, let's say go underneath the water, right? Aren't the two indices of refraction like 1.33 and 1.5? And those are closer together. So do you think there's going to be as much refraction? No. So is there going to be as much magnification? No. So underwater, it will magnify less. You guys got that? Less underwater? The fundamental force underlying all chemical reaction. Hey, we just talked about this with the quantum journals. You guys remember 4 fundamental forces? Which fundamental force of nature was responsible for pretty much all of chemistry? Which one? Electrical, right? I think I told you guys electromagnetic. They're same idea, right? It has to do with something to do with like valence electrons, how the periodic table is organized. That's all electromagnetic force, electrical force, isn't it? Okay. To be safe in the unlikely case of a lightning strike, it is best to be inside a building framed with what, wood or steel? Steel. Ah, right. That could be called a Faraday cage, because that steel would provide a path of least resistance for the electricity to flow through. Okay? So, like, if you were in a building framed with wood, then you might be the path of least resistance, and that would be bad. But if it's steel, the electricity, oh, that's the way it wants to go. Okay? Hey, are we sitting right now in a building framed with steel? Yeah, modern building codes. Like, we know this now. If lightning strikes the building, are you pretty well safe inside this building? Yeah. Okay. 2 charges separated by 1 meter exert a 20 Newton force on each other. If the charges are pulled to 2 meters, do you guys see we just doubled the distance? Right. Now, what's the force on each charge? So let's go pull up these electricity posters. Right. Hey, you guys remember Coulomb's law? Right. So the force between 2 point charges. Now I made these opposite charges so they attract. If they were the same charge, they'd repel. But the magnitude of that force still follows this expression. Right. You got electrostatic constant, multiply the charges together, divide by the distance between them squared. Ooh, this reminds me a lot of universal gravitation. Remember G(m)m over r squared was also a force? Okay. So this question, the premise is we're going to double this distance. Guys, if you double this distance, we're going to double this distance, right? Is that a factor of 2 less d? Because what is a factor of 2 squared? Is that 4? And it's 1 over that. Ah, so what's the new force? 1/4 of the old force. It has to be getting weaker, they're getting further away. It's the inverse square law. 1/4 of the force. Is that true? Right. What else we got? Electrical resistance. Whoops, sorry. So just to complete that. Now, you guys will get different numbers on your questions, but if mine's 20 newtons, guys, what's 1/4 of 20 newtons? That'd be 5 newtons. Okay, so if I had these numbers in front of me, right? Okay, electrical resistance in a wire depends on that wire's what? Do you guys remember doing a Play-Doh lab, the resistivity of Play-Doh, right? So here's some general wire, right? You can have some length, it can have some cross-sectional area, it can have some resistivity, maybe a material property, aluminum versus copper, right? And you guys made Play-Doh cylinders that were just like a blown-up version of that. Okay? You guys remember like putting an LED here, you connect the wires and the LED would turn on because the electricity was flowing through the Play-Doh. Right? Because Play-Doh is conductive. And so what determines the did you say the resistance? Yeah, electrical resistance. That's R, electrical resistance. Okay. Well, do you guys think the longer the wire, the more the resistance? That's a direct relationship. You guys think the thicker the wire, the less the resistance? It's like inverse relationship. And also this material property, the resistivity. In your Play-Doh lab, I think you guys got like 0.25 ohmmeters or something like that. Okay. Right. Now, the answer choices that you guys are going to see are length, check, thickness, check, and conductivity. Conductivity is just the reciprocal of resistivity. So it's getting at the same idea, some material property. All right, you guys can do this? All right, is everybody good? All right, compared to thin wires, electrical resistance in thick wires Ooh, let's look at thin versus thick. Right. So if you blow up this cross-sectional area, the area is larger, larger, larger. What happens to the resistance? It's smaller and smaller. That's an inverse relationship. You guys see an inverse relationship? Right. So it's less in thick wires compared to thin wires. The primary reason a bird can perch harmlessly on bare high voltage wire is, let's check this out. Throw this up here. Okay. So let's say you got a couple of utility poles. There's this electrical wire going between them. This bird comes, puts 1 foot down here, 1 foot down here, and this whole wire is up at 100,000 volts. Right? You guys get the premise? 100,000 volts. Right? Guys, what is the potential difference between 100,000 volts and 100,000 volts? Zero. And isn't it actually the potential difference that determines how much current flows? Well, that and the resistance. If you go back to Ohm's law, right? Current is voltage difference on resistance, right? Okay. A lot of times I leave out the delta for the difference, but that really is an important part of this, right? Okay, so 0 volts. There's no potential difference. Okay, you guys see that? So back here. Oh yeah. So there's no potential difference between the bird's feet. Right, you guys get that? When an 8-volt battery is connected to a resistor, 2 amps flows through the resistor. Oh, get back here. What is the resistor's value? 8 volts, 2 amps flows. Hey, does that sound like Ohm's law? Ohm's law? Okay, now where's, oh, am I missing a page here? Okay, here. Right, this up here. Okay. So do you guys remember with Ohm's law? I would usually write it as the current that flows is equal to the potential difference. A lot of times I just say voltage acting on resistance. Right? Is that true? Like that? Right. Or a lot of textbooks or instructors might write it this way. Voltage is equal to current times resistance. Right? You guys remember that? That's Ohm's law, right? Ohm's law. Right? Everybody good? Right. Any question? Okay. So if you're solving for resistance, can I just do voltage divided by current? Divide the current down? I is current, right? Measured in amps. Right? Okay, so that's going to bring us to this. Right? I got 8 volts. 2 amps ends up flowing. So what's the resistor that made that happen? 4 ohms. You guys see 4 ohms? You guys can do that? Right, are we good? All right, Ohm's law. When connected to a 110-volt power supply, how much current is in a light bulb with the resistance of 220 ohms? Okay, so how much current? Hey, that was the way I originally gave you Ohm's law, this fraction form. Current is potential difference acting on resistance. Isn't that right? Okay. So we've got 110 volts. We got 220 ohms. Does that result in half an amp? You guys see half an amp? Right. You guys can do Ohm's law, navigate Ohm's law. Right. Real short equation. We've used it a bunch in this class. Okay. You guys see that? All right. 80. A light bulb is plugged into 120 volt outlet and 0.7 amps of current flows. What is the power rating of the bulb? Ooh, this sounds like Joule's law. Fine. You guys remember Joule's law? This is one form of Joule's law. Power is current times voltage. You guys remember filling out all those Kirchhoff tables? And the last column of the Kirchhoff table was always that right there. If the power is current times voltage. Okay, you guys remember that? Okay. So they just told us the current and the voltage. They said 0.7 amps of current and 120 volts. Right? Isn't that true? Right. So how many watts of power is that? Got 84 watts. Right, you guys got 84 watts. Right, any question? Any question? Right, you guys do good? Right. Joule's law. Right, now, of course, when you guys get the exam, the numbers will be different, but they'll still be Joule's law. That's current times voltage is power. E equals IV. A closed circuit is one in which current what? Right. Here's open and closed. Ooh, that could be like a flashlight, possibly. I got a battery here. I got a light bulb here. Could be a light bulb, right? And ooh, maybe I got a switch up here. And here's the closed switch. Here's an open switch. Here's a closed switch. Hey, doesn't current flow in the closed circuit? Oh yeah, no. Yep, same order, same order. Okay. Right. So current can flow in a closed circuit, right? As more lamps are put into a series circuit, the overall current does what? Let's check that out. Right. So more and more lamps in a series circuit. Right. So I got 12-volt battery here. Guys, suppose I just started with 3 ohms, like 1 resistor, right? Wouldn't the current from just one be, okay, I got 12 volts acting on 3 ohms, that'd be like 4 amps. Right. Now let's throw a second guy in the mix. Now I got 2 resistors. Guys, what is 3 ohms and 3 ohms in series? What is that? 6 ohms. You could just add them as long as they're in series, right? So now I got 12 volts acting on 6 ohms. That's 2 amps. Hey, did the current just go down because the resistance went up? I think it did. Right. Let's throw in one more. Let's throw in the third guy right there. So now I got all 3 in the mix. Right. Guys, what's 3 plus 3 plus 3? 9. So now I got, okay, so same 12 volts battery acting on 9 ohms. That's like 1.33 amps. Do you guys see the more and more the resistance, the less and less the current? You guys see that? Right. Are we good? Right. Who got any question? Any question? Right. All good. Right. As more and more lamps are put into a parallel. Oh, back up. Sorry, there's one more thing I meant to ask you guys. Right. As you put more and more bulbs in series, what happens to the brightness of each bulb? Gets dimmer and dimmer. You guys remember that too? Right. Okay. Right. Now we're ready for the next one. More and more lamps in a parallel circuit, the overall current. Okay. So let's just start with where we started before. Got 12 volts acting on those 3 ohms. Isn't that 4 amps? 4 amps. Okay. Now I'm going to add on another one in parallel. Ooh, well, there's still a 12-volt drop across this one. So isn't that also 4 amps across this guy? And if I throw in a third resistor, now it's another 4 amps across this guy. Okay. Now remember, amps to measure current, that's sort of analogous to like water flow, like gallons per minute, or you can say like traffic flow, like I got 4 cars here, 4 cars here, 4 cars here. Okay. So every time I add on another resistor in parallel, isn't that more current that's being supplied by the battery? I got 12 amps of current, as you guys see it right there at the end. But 12 amps, right? 4 is 12 amps. Okay? And every time you add on a bulb that way, what happens to the brightness of each bulb? Stays the same. Yeah. Remember that? Guys remember that? When one bulb in a series circuit containing several bulbs burns out. Let's check this out. All right, so let's go back to our straight series setup. This is series. All right. And let's say this guy gets knocked out. Bonk, he's gone. Did that just open the circuit? And are those other 2 bulbs even going to light up? No, they're not. So all the other bulbs turn off. Right. Now let's go to the parallel circuit. Right. To the parallel setup. Right. What if you knock this guy out? Bonk, he's gone. Hey, is there still a path for the current to flow through the other 2? There sure is. In fact, did they even change the brightness? No, they don't. It stays as bright as they were before. No change. Right? You guys can do that. Right, are we good? Okay, any question? Any question? There we are. A short circuit occurs when? Is that when a positive wire? Oh, zoom in. You guys can read this. A positive wire is connected directly to the negative, or it should say positively connected directly to the negative lead. I think that's what we're looking for, right? Positive connected directly to negative. That's called a short circuit. Okay? If you take a battery and you take a paperclip and unwind the paperclip and just took the positive directly to the negative, you just created a short circuit. You probably don't want to do that because it'll get really hot really fast and it'll drain the battery really fast too, right? Okay. What's the total resistance of 10 ohms and 7 ohms in series? 10 and 7 in series. Okay. Let me bring up a poster. Maybe I should have brought up before. Where is my resistors in series? Here's my resistors in series. I see 3 resistors in series right there. All right, I see that. All right, so you could just add them up. Very simply add them up, right? We just did that a few minutes ago, right? Just add them up, right? So what is 10 and 7 in series, boink, boink, 17. Isn't that true? 10, 7, 17. All right, guys good? Any question? Any question? All right, next. When 6 and 12 ohms are in parallel, guys, 6 and 12 in parallel. Okay, no, let's take a look at parallel circuit. Parallels. Hey, I showed you guys two different ways to do this. You could add fractions together and take the reciprocal of the reciprocals added together, right? But we didn't do that very often. What we normally did was just look at two at a time and do product over sum. You guys remember that? Do product over sum for two at a time, right? Okay. And that, let's do product over sum of 6 and 12. Got 6 times 12 over 6 plus 12. Is that like 72 on 18? That's like 4 ohms. Can you guys do product over sum for two resistors in parallel? You guys can do that, right? All right, any question? All right. If you break a bar magnet in half, each half, hey, remember I gave you guys a stack of bar magnets and it effectively acted as one giant magnet. Then you can like break that second half and each half had its own north and south. Guys, can you ever break a magnet in half and there's only one pole on one and the other pole on the other? No, you always get two poles. You always get a north and a south. Okay, so each becomes a bar magnet with two poles. Right, guys got that? Number 90, a device consisting of a coil that is mechanically rotated in a stationary magnetic field. Actually, let's do these next two together. The one after that says a device that transforms electrical energy back into mechanical energy. So let's take a look at the poster that has both answers on it. You guys remember this poster right here? You guys remember that one? Right. So a generator is when you take mechanical energy, let's say like water falling on a waterfall, could turn this water wheel. It's going to force this wire to rotate in this magnetic field, which is going to force electrons to move. And now you have electric current. Now the energy that used to be in the falling water, in the waterfall, it's been transferred into electrical energy. That's a generator. Okay. The other half of this story is, okay, now we got electrical energy. Now we're going to take that current, flow it through this wire that runs it past the magnetic field. That creates a force. Like both of these involve the right-hand rule, just different ways. Okay. Okay. So that creates a force. That creates a, now we get mechanical energy out. That's going to turn the ceiling fan. That's a motor. You guys remember a generator and motor? Generator, motor? Okay. And that's these two answers right here. So if we're going from mechanical to electric, that's a generator. If we're going electric back to mechanical, that's a motor. Most commercial generators are driven by, how do you get energy from coal or nuclear? It goes through which process? Steam, right? Yeah, you boil water. So how do you get energy from coal? You boil water, turns steam, turns a turbine. How do you get energy from nuclear? Run a nuclear reaction, boil water, turn to steam, turn a turbine. Okay. There are some exceptions, but that's how most electricity is generated. Light behaves as a, we're on to the last section. We're on to quantum mechanics. This is it. It's the final stretch right here. Guys, is light a wave, a particle, or both? Both. So remind you guys of history. This was a question for hundreds of years. There's Young's double slit experiment. If you shine a light through double slit, it makes an interference pattern, which would indicate that it's a wave. But then along comes Heinrich Hertz with this photoelectric effect. And then Einstein explained this and said, hey, this direct relationship between the energy and the frequency indicates that light also has particle-like properties. Call those particles photons. Right? A photocell can be activated with blue light, but not red light. That looks consistent with what I just showed you. If it's a high frequency, maybe you can get some energy out of it. Like blue light has a high frequency compared to red light, might not be high enough frequency, so you get zero energy out of it. You see, red could be here, blue could be here. Right, you see it? So the Okay, this is because blue light has, so what did I just tell you? That blue has a longer wavelength than red light? That's exactly backwards. Blue light has a higher speed than red light. Guys, do blue and red light move at the same speed? Same speed of light. So stronger electric field, a higher frequency. Bing. That's exactly what we're looking for. A wavelength of a particle is called the de Broglie wavelength. You guys remember this? So de Broglie comes along, says, well, all this stuff. Here's the wavelength of any particle. So now we have, now particles have wavelengths. Wave-particle duality. You guys remember de Broglie? Remember that? Right. And this was particularly important for electrons because electrons have such a small mass that that wavelength becomes important enough that you get this phenomenon right here. Actually, I think this is leading to the next question. You guys remember electron waves? Right. So electrons can only occupy certain orbits, certain energy levels. Why? Well, because they have to complete wavelengths, because they have wave properties. Right. Energy levels, the whole deal. Right. Valence electrons organizes the periodic table. Right. So let's check this out. The wavelength of the discrete orbits in electrons are best understood by considering the electrons' what properties? Wave properties. Wave properties. Right, that's what I just told you. Wave properties, right? You guys got that? Right, every good? All right, these last four, let's read all four of them and we'll knock them out all together. Nuclear fission occurs when? Nuclear fusion occurs when? The primary nuclear fusion reactor, the primary fuel for nuclear fusion, the primary process, a nuclear process that involves or has relatively few radioactive byproducts. Okay, so these are all nuclear reactions. Let's look at the poster that had both types of nuclear reactions on it. Right, you guys remember fusion and fission? Okay. Now, this graph shows binding energy per nucleon as a function of mass number. So binding energy depends on what atom you're in. Okay. If you're starting with iron and you're trying to get nuclear energy out of that, then you're out of luck because whether you do fusion or fission with iron, that only absorbs energy. So that's no good. But if you have uranium, you can bombard uranium, you can split it, and you can get a difference in energy. That's how you get energy from a fission reaction. That's fission, right? Splitting uranium, right, or plutonium. Right? Now the opposite process over here is fusion, and now anything can do well. Fusion goes all the way up to iron, right? But the main reaction we care about is hydrogen to helium, and actually it's specifically these isotopes of hydrogen, deuterium and tritium. You got like extra neutrons. Is it? So, what are we looking at here? Fusion. Okay, we fuse together hydrogen and make helium and release a ton of energy. Actually, this is like hundreds of times the energy. It's like almost 1,000 times the energy. Okay. Now, fusion is a developing technology. It isn't quite cracked yet. Because all the nuclear power plants we have in the world that are commercial are all what type of power plant? They're all fission. They're all fission, right? Fusion, yeah, it's getting close. It's getting close, right? And supposedly, according to what I read, the world's oceans are full of these isotopes of hydrogen. Right? So, like plenty abundant enough that it'd be pretty much anything we'll need for like here on out. All right, so let's look at these questions again. Fission occurs when? Let's go with. I'll tell you guys the answer to this one really quick. Guys, write down this one or choose this one. Electrical forces inside a nucleus overpower nuclear forces. Right. Otherwise, it may not be obvious. That's what we're looking for. Right. Guys, choose that one. Nuclear fission occurs when electrical forces overpower nuclear forces. Can you guys see that? Right. Are we good? Right. Nuclear fusion releases energy when? Do you guys think very light nuclei fuse together? Yeah, anything smaller than iron, pretty much. Right? Most notably, hydrogen to helium. Right? That's the energy of the sun, too, isn't it? Hydrogen to helium. Okay. The primary fuel reactor for fusion is what? Fusion is what? Hydrogen, right? Right? And a nuclear process that has relatively few radioactive byproducts. Relatively few radioactive byproducts is which one? Fusion or fission? Fusion. Okay. Right now, all our power plants are fission reactors, and one of the problems with those is there's lots of radioactive waste we got to figure out what to do with. But fusion is a lot cleaner. Okay. Guys, okay. All right. Actually, that takes us right to the end of class. So I'll show you guys paper roller coasters tomorrow, and yeah. You guys are ready for the exam.